Yes. What? Is there a switch? Is there a switch? Okay, good. Okay, great. We're going to start back up. I hope everyone had a nice lunch. We had some excellent presentations this morning from different points of view, from the public, industry, emergency responders, standards development organizations. And this afternoon, we're going to be talking about different technologies. We have a panel here that's set up, marine bunkering, and we're going to hear from our Office of Hazmat Safety, and then we're going to have an open discussion to wrap this up. So I encourage you to have a lot of questions for the open discussion that we're scheduling here for 3:30 until the end of the day.
Good afternoon. Our next guest speaker will be Greg Denton. Greg Denton is Business Development Manager at GTT North America. Greg has spent his career in the oil and gas industry, developing international upstream assets before transitioning to liquefied natural gas business development. Greg began his career with ExxonMobil Development Company in the offshore fabrication department, executing deepwater projects in West Africa. He transitioned to the onshore construction department, where he was seconded to Imperial Oil Resources for Phase 1 fabrication of the Kyrle Oil Sands project in Alberta, Canada. He subsequently joined Hillcorp Energy Company based in Houston, Texas, developing unconventional assets and optimizing the production of both oil and gas plays in the central Texas region. Greg joined GTT Gas Transport and Technagaz in 2012 and has served as Business Development Manager for GTT North America since the subsidiary was established in 2013. In addition to GTT's core activities of LNG carriers, very large ethane carriers, multi-gas carriers, floating LNG units, floating storage and regasification units, and onshore storage tanks, he focuses on the development of the LNG as fuel value chain. Greg graduated with honors from the University of Kansas in 2005 with a BS in mechanical engineering and a minor in Germanic languages. Please welcome Greg Denton.
Good afternoon. It's a pleasure to be here today with those in attendance and those via webcast. Firstly, let me thank PHMSA, the team organizing this, specifically Julie, and congratulate you on a successful event so far. I'm pleased to be here on behalf of GTT to lend our expertise in the membrane storage technology as part of this technology panel, and that membrane storage technology is something that's been incorporated in the NFPA 59A since 2001. So we'll look at the items to cover here today. I'll introduce GTT, Gas Transport, and Technagaz. Certainly speak to our expertise. I thank Margaret Doyle, who'd spoken earlier, to give reference to the first of its type LNG bunker barge that's currently under construction that will support the tote LNG fuel program that we heard some about this morning. But today I'll focus more on the onshore storage technology and define that, how it's considered within the standards, how the membrane technology compares to what's called the 9% nickel technology that is currently referenced in the 2001 revision of NFPA and therefore the CFR, and then speak to the handling of the technology and other international standards, and then the onshore project references we have to rely on. So again, the most efficient way to introduce GTT is I will ask to play the short corporate video to give some perspective.
You can't see us, but we're here at the heart of this giant LNG carrier, at the heart of a technological revolution that makes it possible to transport in liquid form the third most utilized source of energy in the world, natural gas. To optimize storage and transport, its volume is reduced 600 times by chilling it to minus 163 degrees at atmospheric pressure. It transforms from a gaseous state to a liquid to become LNG. Our technologies are here to confine it in a secure and economic manner. World leader in the design of cryogenic membrane containment systems for the past 50 years, GTT has conceived and developed the most reliable systems for maritime and fluvial transport of LNG, as well as storage systems on land or at sea. Our technologies have become benchmarks in the domain of maritime transport and the LNG industry. Highly adaptable, they are also suitable for other liquefied gases. Each of these technologies is certified by international classification societies. Our expertise and our ability to innovate mean we can respond to a wide range of demands across the entire LNG logistical chain. Thanks to the sophistication of our testing methods, to our knowledge of materials, and our diverse technical competencies, we master our clients' most complex operational issues. Highly flexible, our technologies can equip vessels of all sizes. Today, our cumulative experience allows us, via our innovative solutions, to take a leading role in the new LNG fuel revolution. LNG as a fuel is a cost-effective solution and advantageous on an environmental level for the propulsion of maritime vessels. GTT accompanies this revolution by adapting its technologies from containment to propulsion, allowing the cargo space inside vessels to be optimized. With the systems we have developed, we can now offer solutions for the entire LNG fuel chain. Solutions for the fuel tanks in vessels transporting merchandise such as maritime and fluvial container ships, as well as solutions for passenger vessels such as ferries or cruise ships. We also provide numerous technologies for the development of LNG logistics infrastructures such as bunker barges, refueling vessels, transfer arms, and small onshore tanks. For 50 years, GTT has accompanied each of the players involved in the transportation and handling of LNG cargo: ship owners, classification societies, shipyards and repair yards, and oil and gas majors. We assist our clients throughout the lifetime of their vessel, and thanks to our dedicated services, our teams are available around the world to facilitate and optimize all your operations. GTT is ready to accompany you in your projects by placing our experience, our expertise, and our teams at your service.
Excellent. Well, as we saw there, GTT as a company has been linked to the LNG industry and its growth over the past 50 plus years. Our strongest market presence over that time has been the containment system on LNG carriers for cargo transport. You see a breakdown here of the global fleet currently for LNG carriers and the number of vessels on order by different technology type. That means that we currently enjoy a market share of about 3/4 of the global fleet of LNG carriers, and an even higher number for those on order, whether it's the Mark III system or the NO96 system in LNG carriers. In addition to that, the first 19 floating storage regasification units that have been new built specify that same technology. And the first 3 floating LNG projects, the Shell Prelude that you may well have heard, and also the first 2 Petronas projects specify that membrane technology. And something to keep in mind here is these are maritime assets that are designed to operate in harsh, dynamic, evolving environments for 40-year life cycles or 25-year design lives for floating LNG projects. That same technology, what we'll call the Mark III system, is adapted for land storage, our GST technology. And that same Mark system has been proven in operation for 34 onshore storage tanks now in surface, the first back as far as 1972. So that's what we'll focus on today, is specifically these onshore projects and how the membrane technology is a part of that. Globally, there's roughly 100 membrane tanks, onshore tanks in service, and 34 of those are the GTT membrane. Of those, 31 store liquefied natural gas, the others LPG and ethylene. That first tank was built in Europe in 1972. It still operates today. And the range of capacities for these membrane onshore tanks is between 8,000 cubic meters up to 250,000 cubic meters. It's worth noting that there's roughly the same amount of service years that have been accrued with membrane storage technology as with the 9% nickel, the alternative full containment technology. And I'll emphasize again that over 150 LNG carriers use that same Mark technology, just like Chevron's Asia Vision that we saw in the Schneer video earlier today that off-took the first cargo. That was a Mark III technology carrier, and that same system is what's adapted for the onshore technology. Right now there are 2 large tanks under development, one in the Philippines and one in Indonesia, that have been under construction. So with that background, we'll define the different tank technologies and understand how they compare technically. You see here, according to the European norm, the European standard 1473, we have the differentiation of technologies between single containment, double containment, and full containment. With the membrane technology in the right column, you see the consideration is for a full containment tankage. For the sake of this discussion today, I'll go into some more thorough elements comparing that with the other full containment technology, 9% nickel, which involves a nickel inner tank independent from the concrete outer tank. So let's look at the components for the membrane system and see what we're talking about here. For a tank technology, we envision a concrete outer tank, which could also be steel, but this is what you see on the right. And the insulation system that's integrated inside the tank is adhered directly to that wall and is based on prefabricated polyurethane foam panels. These provide the strength of the system and also the thermal performance. The primary membrane that you can see there consists of a metallic stainless steel 304L, which has a nickel composition of roughly 8 to 12% nickel, so it's comparable in that performance to the alternative technology. As you see in the panel to the right there, that cross-section involves a proprietary composite secondary barrier, which performs the thermal corner protection at the corner of the tank, which is required beneath a 5-meter height. Above that, the foam panels do not require that secondary barrier. These components are continuously being built by suppliers and an existing supply chain under watch of classification societies that are to be deployed and installed in over 50 LNG carriers under construction today. So we rely on the exact same components that are proven under harsher environments in marine assets. We'll do a bit more detail here, comparing those two technologies. Again, if we look at the left, a 9% nickel technology is defined in the 2001 revision of NFPA 59A, and therefore is also in the CFR. And the membrane technology, again, is under consideration for that as being included in the 2016 revision. Functionally, we'll compare the concrete outer structure, both for the nickel and the membrane, provide a structural load, or the structural function. With the nickel technology, however, the inner tank consists of 9% nickel plates, both for the periphery and also for the floor. Whereas in the membrane system, again, you're looking at a metallic primary membrane that ensures liquid tightness and gas tightness. In the annular space for the nickel tank, the insulation agent is a perlite or a glass wool, whereas the insulation agent in the membrane technology is that same polyurethane foam panel. The components for the suspended deck are similar for a glass wool suspended deck. However, there's no requirement for rigid cellular glass on the bottom or for an additional nickel thermal corner protection, as is the case with the nickel tank. Again, that is ensured by the integrated secondary barrier in the membrane system that is the same secondary barrier that's required throughout an entire tank in an LNG carrier. One additional element worth noting is the insulation space in the membrane tank is inerted under a nitrogen atmosphere, which is not the case in a nickel tank. That annular space full of perlite is under a methane atmosphere. So with the membrane system, you're able to remove that methane through the nitrogen system. Now the design of the membrane is slightly different. It's an integrated system that has to encounter and accommodate both internal and external loads, and it does so differently than the nickel system. The internal loads that would be encountered are the LNG hydrostatic pressures, as well as the vapor gas pressure. And of course, external loads are risks to impact, blast, fire, these sorts of things. So that's accommodated in a number of different ways. The gas and liquid tightness is ensured by that tight primary metallic membrane. The insulation system is strong enough and is designed to transmit that structural load to the concrete outer tank. And that outer tank also provides the structural resistance and the strength and protection from outer loads. The thermal protection system, as I'd mentioned earlier, ensures that that concrete outer tank corner is protected in case of a leak to the primary barrier, which is a critical function to ensure the integrity of the concrete. And lastly, that insulation system is also what limits both the boil-off rate and the exchange of cryogenic material, cryogenic temperature between the LNG and the concrete. So that integrated system is why the technology is built and constructed the way it is. This separation of functions also ensures that there's no simultaneous catastrophic failure between the insulation and the structural functions. So that's why we have a corrugated membrane. This primary membrane, the corrugation pattern ensures that it's insensitive to thermal loads and can account for those thermal cycles during the loading and discharging process within the tank. You see here how the corrugations are arranged. It's a crossing of the large corrugations and small corrugation. And that knot there, during the fabrication process, the primary membrane, this stainless steel, is folded, it's not stretched, so there's no inherent weakness in that knot. It's able to have the same thickness throughout the knot as in the balance of the sheet there. We also see that the welding of the primary barrier membrane is a seam weld, and welding those elementary sheets together ensures that there's zero stress in the primary membrane there. That ensures that there's almost an unlimited resistance to fatigue and almost no risk of crack propagation in case of a failure in the metallic membrane. So from a safety standpoint, where does that leave us? Where do we stand? The culmination of all of those functions ensure that the membrane technology is equivalent or even superior in terms of safety and risk performance. We have here a breakdown of a quantitative risk assessment that was conducted by ESR Technology in 2011. ESR is a third-party independent firm that was formerly the Engineering, Safety, and Risk business unit of the Atomic Energy Authority within the UK. And they evaluated all these listed external LNG release causes, as you see, between the membrane technology and between the 9% nickel technology. And what was found is, of course, that the membrane and that 9% nickel, those tanks are predicted to pose a similar level of risk from all external leaks. The critical element more is the design of each tank against specific events, which is more important in the concrete outer tank. So with that comparison between the technologies, let's discuss how the membrane technology is referenced in other relevant international standards, as is the case throughout the world. You see here that the membrane is now included in all relevant international standards, that the United States will be the final link in that. And with the revisions here in 2007 for the European norm, forthcoming revision in 2016, we'll consider membrane within full containment with no longer a differentiation between that. It will be single containment, double containment, full containment, and membrane is just interchangeable with 9% nickel. Also, we see that the NFPA 59 2016 revision defines the membrane and considers it equivalent from a risk perspective. As we define there, that means that both are considered equivalent safety and therefore have the same requirements for performance. Moreover, both systems are now able to be designed without a dike, which is no longer a requirement for these full containment technologies. And other recent updates specify similarly no requirement for a dike in both the Canadian and the Korean standard. So I'll conclude by focusing on the many onshore tanks that have been in operation for over 40 years to demonstrate the reliability of the technology and the capability of the technology. This is an index here of the 31 LNG tanks in operation specifically, the first in 1981. These are, of course, available on GTT's website you see there. If you have any more questions, and of course the largest up to 200,000 cubic meters for these type of above ground tanks. And I'd mentioned earlier two specific onshore construction projects underway. We see here a 130,000 cubic meter deliverable volume for a regasification project in the Philippines. The concrete outer tank has been completed and the containment system pre-production is underway. In the lower two pictures you can see those kind of prefabricated panels we're talking about that will be installed inside the tank. It's worth noting that this project in the Philippines and also the tank you see here in Indonesia are in heavily seismic areas that encounter loads that would require slab isolators for a nickel technology tank. That's not necessary with the membrane technology you see here. We have a 90,000 cubic meter working volume tank in Sengkang, Indonesia for the liquefaction plant portion of the same project. And the concrete has been completed and that moisture barrier that precedes the containment system installation will begin soon. So from a standards perspective and a references perspective, Why is this relevant now? Why is industry requesting this technology? And there's a number of reasons. Firstly, it's proven. We have over 34 tanks in operation, as you see. It's referenced in all relevant standards. We have the feedback of 150 LNG carriers in operation with that same technology. And the modularization of the system ensures that there's reduced construction cost and reduced construction schedule. So the project is to market sooner for a lower overall cost. And that's a benefit of this repeatable automated system. So you have no requirement on specialized labor. You're able to rely on automated trainers with automated equipment operators with the support of GTT. And from a design perspective, the installation system design does not change. It simply grows in volume. It's very scalable. So that's why we see a real urgency to include the technology in the latest standard, because it's of interest to industry. So I'll just wrap up with what I covered throughout my discussion today. The membrane technology is now broadly recognized by all international standards, including here in the United States. It achieves a similar safety and risk performance as the technology that's currently referenced in the CFR, the 9% nickel. Because of that transfer of loads to the concrete outer structure, it's a slightly more robust concrete outer design than the other technology. It has benefits of 40 years onshore performance feedback, but more importantly, there's the benefit of 150 LNG carriers with that same system operating in harsher dynamic environments for a longer design life. And during the erection process, there's continuous testing to ensure that the erection is done properly and that integrity is ensured at each step of the erection. And ultimately, it delivers more value to the market and to the industry, the project developers who are requesting this. So, thank you very much for your consideration.
We'll take some questions for Greg.
Hello, my name is William James. I'm from Central Florida, and the construction of your tank is admirable. As you know, Florida is kind of unique with their sinkhole problem, and you can't predict where a sinkhole will happen. And with the growing LNG industry in Florida, storage containment tanks could be a big problem. Have your engineers figured in this that a sinkhole could properly happen under a tank, and the center of that tank could disappear without warning? We lost Porsche cars down there. We lost houses down there. Swimming pools, lakes have disappeared. What could happen to an LNG storage tank?
Thank you for your question. It would be necessary to ensure that a sufficient seismic and foundation and civil analysis is done to ensure that is a safe slab, a safe foundation beneath any type of tank that's built to overcome anything that might happen.
Yes, good afternoon, everybody. My name is Aziz Bamik and part of GDT. Just maybe to complement the feedback experience we had in real life. You know what's happened in March 2011 in Fukushima with the earthquake. So the feedback I can share with you is that most of the piping around the tank was damaged. The tank integrity remained intact. So of course we will do a lot of studies, but we have this kind of feedback from accident that occurred. And you know the earthquake of Fukushima was, I would say, at very high intensity. And all the tank system and tank storage remain fully intact and in line with the codes and came back to the operation after the accident.
All right. Thank you very much.
Our next speaker is Alan Hatfield. Alan Hatfield is Vice President of LNG Technical Services for Braemar Engineering in Houston, Texas, with 35 years of natural gas and LNG experience. Alan started working with utility peak shaving in 1985 with propane air systems, and in 1988 as LNG plant manager at Columbus, Georgia utility peak shaving facility. Alan Hatfield's next stop was with BG as engineering manager for Atlantic LNG in Trinidad and Tobago, where he lived from 1998 to 2002. Alan was director merchant LNG for El Paso in 2003, with primary responsibility for development of the shipboard regasification systems for accelerate ships, a first of its kind. His next position was with Marathon Oil for the Equatorial Guinea LNG liquefaction project. Following that, he worked for Cheniere as project manager of Corpus Christi LNG and providing support to Sabine Pass and Creole Trail LNG for 4.5 years. He has worked for Braemar Engineering since June of 1988 and led numerous large and small-scale projects and studies. He is currently on the NFPA 52, NFPA 59A, ACI 376, and AGA Supplemental Gas Technical Committees. Alan has a BSc in Civil Engineering from University of South Florida and a PE license in 6 states. Please join me in welcoming Alan Hatfield. Why don't you just hit one and see what goes?
Okay. Hello, I'm Alan Hatfield, Braemar Engineering. I was invited here today, I guess, for my participation in the AGA committee, the ACI 376 committee, and NFPA 59A. I was involved when a lot of the development took place, interacting with FERC and others during the time that LNG was full containment. Concrete tanks were first emerging in the most recent designs that we'll be talking about today. Nick Legatos with Preload had invited me to be on the ACI 376 committee in 2002. And I've been on it since. We've spent thousands of hours and over 10 years developing the book, and we'll talk about the details in a minute, but I didn't know that that was a lifetime commitment, but it seems to have been. But for most of you, the slides are in this first group, LNG 101, repeating much of what you already know. Just to make sure everybody's on the same page, that refrigerated tanks we're talking about are defined by API 620 as tanks that have operating pressure less than 15 psi and exposed to cryogenic temperature. The current version recognized by DOT 193 is the NFPA 59A 2001 edition, which does recognize concrete tanks, pre-stressed concrete for containment and secondary containment. But the NFPA 59A committee requested American Concrete Institute develop the ACI 376 code because 59A did not provide the details on how to construct a concrete tank. The version that we are using is 2001 with some references to 2006 on the seismic design of tanks. 2009, 2013, and 2016 have been published, but not currently recognized by 49 CFR 193. My presentation does not include the shop fabricated tanks. These are typically stainless steel tanks. They come in a horizontal or vertical design. That's just, they're an option for LNG storage. They're just not part of this. LNG tanks come in many shapes and sizes and configurations. So when you're talking about site fabricated tanks, you have to really get down and identify the type of tank that you're referring to. So we have 3 tank types: single containment, double containment, and full containment. The full containment being the concrete tanks. The double containment typically has an outer concrete wall. The foundations can be at grade. They can be elevated above grade where you have an air gap underneath the tank, or as in the picture from Japan, below grade. These are not found in the U.S. For the, I'm sorry, I skipped over the containment for tanks that exist out there. Aluminum, stainless steel, 9% nickel, or pre-stressed concrete, where the primary container is in direct contact with the LNG. In 59A, there's 3 spill cases that are used to describe the tank configuration for siting. These are used for when you calculate the vapor dispersion and thermal radiation. So you take your tank type and you apply the conditions from the code. So the first one is a bottom withdrawal tank with no in-tank valve, and that's a single containment tank, and so that's a full tank spill is required when you have this style tank. So you take the full content of the tank and you would design the spill containment for that. The bottom withdrawal with an in-tank valve has a 10-minute spill requirement, where if you had a spill, you have a secondary valve that's inside the tank that can be closed externally for emergencies that isolates that, and so the code allows for a 10-minute spill. The third one is where you have no penetrations below the liquid level, and the withdrawal is through the roof, usually with in-tank pumps, and the same 10-minute spill applies. So a single containment tank typically has an aluminum, stainless steel, or 9% nickel inner tank. Usually has to do with the cost of the metal at the time the tank is constructed. But you'll find all of them have been built at some point. The outer shell is carbon steel, is the vapor barrier and pressure containing element. And then it has a detached secondary containment berm, usually earth or other materials. That's designed for the spill case for your type of tank. Full containment tanks typically have a stainless steel, 9% nickel primary liner. There are full containment tanks, though, where LNG is in direct contact with the concrete. It has an integral secondary containment wall, where if the primary tank fails, that the outer concrete wall is designed to contain the cryogenic fluid. And it also has a carbon steel vapor barrier for pressure containment. In the US, the map shows the locations of full containment tanks that currently exist. This is a tank, Philadelphia Gas Works. They have two of them, 94,000 cubic meters, that has pre-stressed concrete walls where LNG is in direct contact with the concrete primary, and it has a concrete secondary wall. These were built in 1974 by Preload. Single containment tanks, where you have we have a bottom withdrawal and no in-tank valve. You're sizing the impoundment for 110% of the full capacity of the tank, which includes the volume of the displaced tank. You also have a 10-minute spill impoundment for smaller spills. Compared that to the for the thermal radiation case, you fill the pool up with LNG then and calculate the heat radiation. The code defines the three zones. You have the closest one is 10,000 BTUs per square foot per hour. That's the zone basically that you don't build anything. For this spill case, you have a 3,000 BTU line, which is where you don't have any occupied buildings within that zone. And then at the property line, for siting, you cannot have more than 1,600 BTUs per square foot per hour at the property line. So this is the worst case here for the design spill for a tank with no in-tank valve. The vapor dispersion looks the same, where you fill the entire dike up with LNG and calculate the vapor. And you have to have enough real estate where the property that can be built upon, that the vapor dispersion does not cross the property line with more than 50% of lower flammability limit of natural gas. For the bottom withdrawal tanks with an in-tank valve or a top withdrawal, you're designing the vapor dispersion for the 10-minute spill case. So the vapor cloud is significantly less. Therefore, the exclusion zones are less and requires less real estate. For full containment tanks, then the difference would be the secondary containment is integral to the primary. There's various designs. I'm just showing one example. In this case here, the LNG is in direct contact with the concrete wall. There is a liner on the outside of the primary concrete. There's insulation, and then there's a secondary containment wall. And the code is flexible in, allowing different configurations for this. For the thermal case, the basis is that the assumed failure is that there's no tank top, that the roof of the tank is gone. There's no penetrations. And so the thermal radiation is calculated. Compared to the single containment tank, the exclusion zones are significantly smaller because of the height, as well as the fact that the surface area is so much less. So for the full containment, the vapor dispersion as well is for the 10-minute spill based on the full pump out rate of all the tanks at one time. And it's calculated where you cannot exceed 50% LFL at the property line that can be built upon. So to get to the point where you have all the cases, typically you do siting studies that often CFD modeling or other models are allowed in the code that take into account the site-specific issues. And you look at many different cases to make sure that none of the cases cross the boundaries of the property line that can be built upon with vapors and thermals, and that's critical in the permitting stage to make sure that the site meets the requirements. This is a very critical point in the permitting process, and so collecting the design data and the climate data and everything else is important. And there's models done on different wind directions and wind speeds and minimal wind and significant wind and different temperatures and humidity, and take into account the terrain, buildings and everything else. And the models then create graphics similar to what you're seeing here that show what the spilled cases, which are dictated in the code. These are prescribed cases that you have to demonstrate that the plant can meet. It doesn't imply at all that they're going to occur. It's just that the code assumes failure scenarios that you have to validate and show that the plant is safe under all these cases, some of them quite extreme. So that leads to kind of a summary then. The single containment tanks are typically located today, under the current guidelines and siting requirements, where you have a large amount of land in rural areas, not a lot of public access nearby, and that you don't have a lot of security concerns, and you would use the API 620 code for that tank. Double containment, there's not many of these, but if you were to choose that design, it does offer some of the benefits of full containment, where you have less real estate. It does offer the concrete walls, so it is more robust, and so it's kind of in between. And typically the primary container is going to be built to API 620, and the secondary containment, if it's concrete, then would be ACI 376. Oh, I'm sorry, I jumped ahead. Then full containment, that's where you have the smaller site. You have oftentimes, waterfront sites just aren't available with huge acreage, and the public it's more congested area, closer proximity, and that if there's a greater security concern, that they offer a more robust design for that, and ACI 376 code applies. So comparing single containment to full, basically the full containment offers the smaller exclusion zones. They require less real estate. They're more robust to security, weather, fire, and the concerns from explosions, whatever. They cost more and they take longer to construct. One example of double containment, I think it's the only example that I'm aware of, in the US at least, is Ecoelectrica. And it tells a good story about the transition from the industry using single containment tanks to now building, at least at the large terminals, in many cases they're selecting full containment. In 1994, Ecoelectrica, which was Enron at the time, applied to FERC to build an LNG plant using full containment LNG tanks. And their application for full containment was denied. And they changed their design then to double containment. And so the drawing that you see is from the EIS in 1996 that shows the design of the double containment PDM built in I got my information talking to Bob Arvelin, who at the time was the director of FERC, and who took an interest in that project and took an interest in full containment tanks, and he just had some reservations. And so I'm more or less sharing with you conversations that took place, one through AGA. He came and spoke to the AGA committee in 1999 when I was the committee chair about the committee's feelings about full containment tanks. He also addressed the 59A committee. He was a participant, and I was too at the time. And we also traveled up to Chicago to CB&I, who made a presentation on the design and full containment tanks. And so I'm sharing with you kind of the concerns at the time. And that was that with single containment tanks, you can identify cold spots. When you first build a tank, sometimes there's settlement issues with the perlite where you can have cold spots, and became clear to clear the cold spots, you would just vibrate the perlite down, and if they existed, and it was easy to see and easy to repair. And when you put the concrete wall up, the question was how do you know they're there and how do you fix them? The inspection of the carbon steel is bare steel in direct contact with the concrete walls. How do you know it's not corroding, and how do you inspect it? And then the word cracking is used in the concrete industry. Cracking, people think of big cracks, and it's actually used in a different context, in the sense that it's more of a granular level, or maybe not even visual, but it certainly does not imply a lack of tightness to the tank. And so those were kind of the issues at the time. And so Ecoelectrica went ahead and built a double containment tank. And Bob said at that time that tank was built that they didn't quite get that right either. That there was issues with the amount of rainwater that it collected, because the entire surface is exposed. It does create some confined space entries issues between the walls, because there's not a lot of space between them. You also have a potential for confined space explosion, where you have, if you had an air gas mixture and an ignition source. And it's a very complex structure, because the tank and the secondary containment walls are self-supporting, they're independent. and so it makes it more difficult to build. And so he, at the time, just said we didn't get that one quite right either. And so more or less since then, all the tanks that have been built have been full containment. And so with the move to the development of ACI 376, starting in 2003 to the first published in 2013, all these issues were addressed and brought to the committee and made sure that there was an answer and mitigated all of them. I don't have time for that, but because I need to wrap up. But the outcome is that 376 is a 149-page document that tells you how to build full containment tanks, and it's in 59A 2016 edition. So if you now build a full containment tank, that's what you'll use is 376. 620 still applies to the metal tanks. And so there's the book's available. It tells you all the details of how to build it, how to commission it. So thank you for your time.
Yes, I'm Jerry Havens, University of Arkansas. I've been working a long time on fire modeling, and as you mentioned, since the advent of the full containment tanks, the worst case design spill now is a roof fire on a tank where the roof has failed. And my question boils down to, and you couple that with the fact that the regulation requires you to consider the worst case to be for high winds because of the proximity of the fire plume to the earth. My question is, if you had a tank top fire in a full tank, which would presume that what you're modeling is that the roof is gone, all the calculations I've ever tried suggest that a full tank would burn for at least a day. So I'm wondering if if anybody has considered whether or not a tank burning full with no top in a 20-mile-an-hour wind would withstand that kind of exposure. Do you know if anybody's even looked at that?
I don't know specifically, but when they do the modeling, they assume that the tank top is gone. But there's no scenario that I'm aware of that anybody's come up with that says how the tank top was removed. It just happens, So that's the scenario that you're given. And so, but as you know, the flame will lift because of the fact that you don't have air-gas mixture at the surface. It has to be high enough where you have mixing, and so the thermal radiation that's produced from that fire is then calculated. But from concrete exposure compared to, say, a metal tank, the radiation is significantly higher rated, as to the amount of heat that it can be exposed to. But, I don't really know the answer other than just how I would approach the analysis of it.
I just want to make clear I'm not disagreeing with you. I cannot imagine a situation where the roof disappears. What I'm wondering is whether or not we are considering, when we move to a full containment tank, and nowadays most of the terminal applications are getting the same answer for the maximum fire exposure range, around about 1,000 feet. Because if you specify this accident, that's the answer you're going to get for the kind of tanks you build. Now my question is, if we are now making the worst case something that everybody agrees they can't imagine how it would happen, are we not jumping off about taking our, worst cases where they're not even best judge. And I know you don't, I didn't expect you to have an answer to the question. I wondered what your opinion was.
Right. I think, as a designer, I'm not given the luxury to come up with the scenarios. I'm just applying what the code says to do. And, but I agree with you that if you were to sit around a room with the best and the brightest trying to come up with a case for how the rooftop disappeared in the first place, I don't think there's many scenarios that are credible, if any. As far as I can tell, these tanks are extremely robust from just about every case.
Questions? Hi, William James again from Central Florida. I hate to play the devil's advocate, but as a citizen, what else I got to do? I assume that these tanks are electronically monitored for safety, levels, spillage, stuff like this. Am I correct? And if it's along the line, but the type of electronics they would use would be digital electronics. Am I correct? As most of your electronics are now today, they're being developed for safety reasons. Now, is the industry aware of, and I'm sure they are, that technology exists to be able to disable digital electronics by the air, which if a foreign government or any kind of entity chose to do that, it could be done by a simple light aircraft. What would happen to the containment tanks that hold this LNG if the electronics, the ability to monitor it, was disabled? This is English technology that was developed 2 years ago, and our government has advanced it quite considerably. And it really has not been addressed as far as weaponry much or anything like that. But LNG would be susceptible to it.
Okay, I'll answer your question. It's, you're right, the tanks are heavily instrumented to monitor all the conditions of the tank and the equipment on it, the pumps and everything. The IO count coming from a tank is a high number. It's got hundreds of, and a lot of times, plants are built with fiber optic networks so that the signals are transmitted over basically glass, where those are inert. But the heart of your question, though, is if you lose power and you disable the instruments on the tank, it's just going to sit there. It could sit there for weeks or maybe longer. I don't know the exact time. Every tank is a little different on the heat leak through the insulation. But the relief valves on the top, they're not electronic. They're mechanical, pneumatic devices that are self-contained that will, if the tank pressure builds, it will release. There's no penetrations in the tank. And so it'll take care of itself even if there's no power or no instruments active forever. There's nothing going to happen to that tank. They're not. It doesn't have a regenerative cooling system on it. It's just a thermos bottle. But right, this one would have less shelf life. But at the same time, the relief valves that protect the vapor space of the tank are not electronic. They are mechanical pneumatic devices that will release the pressure even if there's no power and no instrumentation. And it wouldn't be affected by an EMP or anything else. So it would be safe for an unlimited period of time. And it's actually sized for those conditions. Well, the question is what happens to the methane gas that's released? The plant is built as a closed loop system, and you don't vent unless it's an emergency, and so that's the only time that would happen. It's not good business either. It's not something anybody wants to do.
Thank you, Alan. Our next guest speaker is Matthew Martineau. He is Principal Project Engineer for Chart Incorporated, a subsidiary of Chart Industries Incorporated, a manufacturer of products used in the production, storage, and distribution of liquefied cryogenic gases. Matt works in the Projects D&S Americas group within Chart's Distribution and Storage Division. This specialty group supports customers with turnkey equipment package solutions to solve whatever gas needs they have. These projects include designing systems that store and distribute liquefied gases for end-use liquid and/or gas applications. Industrial gas applications include atmospheric gases such as nitrogen, oxygen, and argon, as well as hydrocarbon-based gases such as natural gas, hydrogen, ethylene, and liquefied natural gas. Matt holds a BS in mechanical engineering from the University of Minnesota and is an alternate committee member on NFPA 59A. In the past 5 years, he has been actively involved in many LNG-related projects in the United States, Canada, and India that include liquefaction, storage, regasification, truck fueling, and transport loading applications. Please join me in welcoming Matthew Martineau.
Thank you. Good afternoon. Can anybody hear me? Oops, there we go. So again, my name is Matt Martineau. I'm with Chart Incorporated. I'm here today to bring the perspective of a manufacturer's perspective as it relates to the topic of referencing referencing of older standards in the CFR 193 and some of the problems it's been causing for us. As a manufacturer, we're kind of caught in the middle between the customer and the regulatory agencies. Many times they trip over these inconsistencies after an order has been placed for equipment that is based on assumptions that we're building to current codes and not to codes that are called out in 193 that references back to, say, ASME pressure vessel code calling out 1992 edition. Primarily, our business is in the small scale, LNG. We do our energy and chemicals division builds heat exchangers that are used in medium to larger scale applications, both in the atmospheric gas side and LNG side. But primarily, our groups work together on a lot of small scale projects. They have, on the liquefaction side, they have systems developed for 100,000 gallon per day, 250,000 gallon per day, 450,000 gallon per day plants. Regasification, we have stationary mobile applications that allow our customers to use natural gas as an alternate energy source for heating and or power generation. Vehicle fueling, we've been involved in that for the last 25 plus years. Trucks, other high horsepower vehicles like mining trucks. We have lots of applications out there serving those applications as well. And we're starting to see more in the rail and maritime, marine loading applications, facilities that support virtual pipelines to move liquid to stranded markets beyond our borders in some cases. So today I'm here to talk a little bit about, well, I know vacuum jacketed pipe and emerging technologies was kind of on the agenda, and I'd like to broaden. VIP is just, or vacuum jacketed pipe is just a subset of a lot of the modular components that Chart manufactures. So primarily what's coming out of our division, we build shop-built storage tanks, unlike the two previous presenters, not site-erected atmospheric tanks, but pressure vessels, shop-built SME pressure vessels. We largely follow the guidance under Chapter 13 for most of our applications, but these days we're finding that those applications are being pushed beyond the volume constraints that are called out. I think 100,000 gallon vessel limitations and 270,000 gallon aggregate storage limitations. If you look within the Chapter 13, all of these applications have setbacks prescribed within them, and then if you build beyond the aggregate storage or utilize tanks that are above 100,000 gallons, then you fall into the Chapter 5 prescriptions, which aren't as well defined for pressure shop-built pressure vessels. So there are some gaps there that we're hoping to close over time in working with our CJ Natural Gas Committee, which Chart Industries as well as a lot of the industrial gas suppliers are members of. That committee, the CGA as a whole, understands that there's a need for the industry, the compressed gas industry, to get more involved with LNG and help form a liaison, I guess, and work closer with NFPA 59A. So, and then some of the changes in the SME pressure vessel code that are hard to get through these days if we're referencing 1992 versions when we're held to building tanks to 2015 edition. If you, technically it's not permissible to register an ASME stamped vessel to a non-current edition. That's mandatory in Appendix 43. But what has been done to register with the National Board to the current code and summarize where the design has been modified or enhanced to satisfy earlier requirements. But that's hard for when you get on site and you're talking to the PHMSA, if in a PHMSA application where the AHJ or the has to then look back to 1992 edition as it's called out in the 2001 NFPA edition and ask us, well, how do we get there from here? And the reality is that what you have to do is you have to understand what the changes are since then, and from the last edition, from the current 2015 edition of the pressure vessel code, there are 77 pages of changes between the 2013 and 2015 edition. So, and that's nearly 1,200 changes. So if you took nominally 600 changes per year, would suggest that since 1992 there are 13,000 changes. Are you going to go through all those changes? No, and you can't. And your vendors, who you have to flow these provisions down to, can't possibly follow the provisions back from 1992. Try to get a hold of a 1992 version of the pressure vessel code. So those are the challenges we struggle with, and would really like to see some updates to reference more current standards. Just to give you some examples of some substantive issues, examples of changes that create measurable differences are the safety factor. There was a change from 4 to 3.5, creating thinner vessels. This was adopted in 1998. The cold stretching of 300 series stainless, code case in 2008. And then you have more recent changes in 2015 that allow phased array UT. So these are all changes that, you know, are keep safety in mind and current technologies relevant to try to build to older editions of the code. What we ideally want to recognize is what are those pieces of older code that are felt to be more safe. Let's identify those. Let's build to the current code and take exception to the current code if we're going to do it that way. With those items that we want, you know, if you want the vessel to be a little bit thicker for whatever reason, let's call it out that way. But to take into to allow us to take into account all of the material changes and changes associated with weld procedure, qualification records, material specifications, UNA forms, nameplate data, all that, we really, you know, need to stick to current code. And as I mentioned before, technically it's mandated. We can't stamp something to an older version of the code. So those are some of the, from the pressure vessel side of things, those are some of the things we're challenged with. What I'd also like to talk about is what's new in terms of equipment is with all the applications that we're serving these days, vehicle fueling, other high horsepower applications. A lot of customers are switching their fuel oil based heating or on-site electrical generation needs over to natural gas, and in those cases where they're stranded from a pipeline, they're bringing it in via trucks in the form of LNG. We're doing a lot of things these days with modular components. So the tanks are considered a modular component. They're shop built. There's a fundamental quality control with shop built equipment versus on-site equipment where you're bringing different people in perhaps to different regions of the country to build things. Harder to control things in outdoor climates, you know, wind, rain, what have you. In a shop-built environment, a lot of that is very controlled. We've done things over and over again. We have in-house quality measures to keep an eye on things, record things, and all that documentation is available during the manufacturing phase. So consistent quality processes and practices lend itself to you know, the small scale applications, building modular components, the tanks, if there's VIP or vacuum insulated pipe involved. We do a lot of pump skids for some of our applications, final line vaporization skids, and we can put all that equipment together for a customer and deliver it to the site, and all they have to do is build the interconnecting piping and get it up and running. So it shortens the construction cycle of a lot of these applications. So in speaking to the siting requirements associated with in these applications that meet the Chapter 13, we're finding what a lot of people will do is try to squeeze in. If they think they're going to go to, if they think they have storage in excess of, say, 250,000 gallons, they will very carefully make sure they choose tanks that are under 100,000 gallons rather than one big tank, because we do make tanks that, you know, up to 1,000 cubic meters these days. Shop-built tanks are exceeding what we ever envisioned would be permissible out of a shop. You could put that all in one tank, but then you exceed the Chapter 13 scope, and then that forces you into Chapter 5 siting requirements. So what a lot of people do is they'll play with that, and they'll build three 90,000 gallon tanks, 270,000 gallons aggregate storage, meet the Chapter 13, and follow all the setbacks prescribed within Chapter 13, and forego any type of vapor dispersion modeling that's called out in Chapter 5, or where it now throws you over into Chapter 15 for doing a qualitative risk analysis. So just some examples of some of the equipment we've been doing lately. I know in the presentation it talked about large bore pipe. I'm actually filling in for a colleague of mine who is going to present pretty much exclusively on vacuum jacketed pipe, but I felt it was important to talk about some of the other modular components that we're doing within the small LNG plant makeup. We do a lot more than just vacuum jacketed pipe, but these are some examples of what was done in a project in Darwin, Australia. Chart manufactured the large bore pipe, the sizes of 4, 6, 12, 20, and 24-inch, 30-inch diameters. These were placed into service in 2005 in Darwin, Australia. Basically terminal piping to get the piping to the vessels from shore. Same thing out here in Freeport. I saw some folks with some shirts that said Freeport on here today, so they're probably familiar with a lot of this piping that's in their facility. And then getting to our storage tanks. This is an example of a 1,000 cubic meter storage tank. 265,000 gallons aggregate storage in these capacity in these tanks. These came out of New Prague, Minnesota. We also build them out of our Czech Republic facility. Here is an example of a 100,000 gallon per day liquefaction and truck rail loadout facility in Miami, Florida. So this customer is liquefying pipeline gas for the purposes of loading ISOs and transport trailers for sale on the open market. And they also have a rail spur off to the right there that once that's active and they have FERC approval, they'll be able to load out some rail cars over there. There is a project, excuse me, not FERC, FRA I meant to say. There is a project that this customer is working on with the FRA to run LNG on a limited basis down a certain limited segment of track in Florida. So here's a different angle of that facility, looking from the tanks up at the cold box. So the cold box is a product of Chart. We manufacture the brazed fin aluminum heat exchangers out of our La Crosse, Wisconsin plant. And the cold boxes are put together, are engineered and by our folks in the Woodlands, Texas, and manufactured the cold box down in our New Iberia plant. As well as the storage tanks here are 90,000 gallon tanks, and you coming off of those and manifolding together, you see some vacuum jacketed pipe. And what you don't see in the picture here in front of it, there is a pump skid that takes the liquid from these tanks and sends it over to a truck loadout facility where the trucks on scales are loaded automatically by weight and then driven off. Another example of a truck loadout facility in George West, Texas, very similar size, 3 90,000 gallon tanks. And you see a better picture here of a little more all-encompassing of the cold box, a couple trailers being loaded on the truck skid. And then a small view on front there, the back of two transports being filled, and the weight of the scales showing up there in the picture. As I mentioned, there's a lot of other applications. We have customers that have had a need to switch the fuels they use in this application. They're running boilers to support their manufacturing processes and save some money. So they chose to go with natural gas. Again, this is a stranded customer in this area of the country. There's not a lot of pipeline reaching them. So they truck it in and they store, there's 8 15,000 gallon tanks, 120,000 gallons total storage, and they vaporize it with ambient vaporizer means and send it into the plant. And then phase 2 of this project, a year later, the customer, they have mining trucks that operate around this plant, and they switched to natural gas burning vehicles, and we plugged in, so to speak, a vehicle fueling subset to this. So it included a smaller tank, a dispenser, pump skid, and it allowed them to pull liquid off of one of these tanks and condition it in a smaller 3,000 gallon pressure vessel, and then dispense it into the vehicle tanks that are on the trucks themselves. And Chart actually plays a big part in that whole product chain there. So we actually make the vehicle tanks that go onto the tractors themselves too. So again, circling back a little bit on the pressure vessel code, as you know, I think a lot of us are singing the same song in terms of the problems created with referencing older editions in current regulations. So we've got referencing the 92 code, and I talked a little bit earlier about the number of changes and the impossibility of potentially trying to sift through all that to try to understand, well, what are the nuggets they want out of this older code? Is there something they want, or has it not just been updated because we just haven't gotten to it yet, or is there actually something there in the 1992 edition of the pressure vessel code that's desired? And if that's the case, then let's fix that. Let's understand what those nuggets are, so to speak. Let's pull them forward. Let's reference current code, but take exceptions to those changes. So we talked about the number of updates and some of the substantive changes in the code, the change in allowable stress and subsequent test pressures, the cold stretch fully adopted in 2008 via Appendix 44. I mean, these are all things we're leveraging today in our products that serve the atmospheric gas world, as well as those customers that are not held to PHMSA regulations. We are, employing the current practices of the code. I wanted to also mention that, or I kind of touched on earlier, that the Compressed Gas Association, being a collection of industry, the industrial gas manufacturers, as well as the equipment manufacturers, as a committee, have been around for a long time, and they leverage their experience in small-scale cryogenic applications and want to do so for the LNG side as well. And they've formed a natural gas committee, and have been in existence now for just about 2 years, a little under 2 years, and they are making a lot of headway in terms of looking at making publications for that we can work together with NFPA 59 and try to make some substantial changes going forward. I want to close with one of the things that Professor Sarah Gossman said earlier, that she emphasized the importance of partnering with the public in the communities in which these plants are being built or targeted, and incorporating by reference older standards during this process can be a hindrance, because they'll pick up on this stuff. As these people, they'll ask questions and they'll read, and as they dig and they see these older references being made, they'll ask questions, and we have to answer honestly that they just haven't been updated, and they're going to wonder why. This can't be that big of a deal to have natural gas and LNG if you can't even keep your references current. So it's a very big deal for us. It's hard to help our customers sift through all this stuff. I kept my notes fairly fluid because a lot of the topics were already discussed today, and I didn't want to overwhelm anybody by repeating information. I'd be happy to take questions if anybody has any questions, but otherwise, thank you for your time.
Well,
I have a quick question. Yeah, that's okay. Yes, Cecile Schofield. I have a quick question for you. Could you please define what you would consider to be a small scale LNG facility that is liquefying natural gas, storing it, and distributing it that would not be FERC or PHMSA regulated?
Well, the definition of small scale, I guess I'll circle back to Chapter 13 and the scope definition, and they define, and they're not using the term small scale. The title of Chapter 13 is stationary ASME applications, something to that effect. So basically what it means, it's a section of the code that's been set aside for products like ours that are shop built pressure vessels as opposed to the larger atmospheric tanks. There was a void in the code up until 15, 16 years ago that there was nothing that really addressed the shop-built pressure vessel codes. So along came this section. It was formerly Chapter 10, now it's Chapter 13, the current editions, and the volume is described as 100,000 gallons per tank, and that was largely picked because back in the day it was assumed that we couldn't build a tank bigger than 100,000 gallons, which we have today, and the total aggregate storage was limitation was 270,000 gallons. So it's either or. You're either at 100,000 gallons per tank or less, with no more than a collection of 270,000 gallons on site. So that's what I guess I would consider small scale in relative to today's topic. As far as where it touches PHMSA or FERC, it really depends on the regulatory bodies and where. I think it was earlier described that basically if it touches the pipeline, either takes gas from the pipeline or sends gas back to the pipeline, it's going to touch FERC. But if it's a self-supporting, the customer we saw with the 8 tall tanks, there's no pipeline there. So they've created their own pipeline. So the PHMSA is not applicable there. They're taking gas, fairly about 1,000 feet away into their plant, self-supported. The PHMSA example the Miami example was a PHMSA application, and my understanding was that was primarily on the fact that they're exporting liquid. They have the ability to export liquid from that facility.
Hi, thank you for your presentation. My name is Harry Kitoma from Exponent. I have a question regarding the vacuum jacketed pipe. If you could just elaborate on the options that you provide and whether you provide continuous vacuum jacketing or whether it is in segments, whether each of the segments are monitored for the vacuum, and whether the vacuum jacketing is designed to contain a leak from the primary containment in the pipe.
Sure. So typically vacuum jacketed pipe is built in segments. The vacuum is not, I think, did you mean dynamically vacuumed where there's a vacuum pump continuously pulling on it?
Whether it's
monitored, okay.
So in answer to your question, what I'm asking is if you have separate segments of vacuum jacketing, whether the pressure in each of the segments is monitored so that you would know whether there is a leak either in the pipe itself or the jacketing itself.
Okay. In most applications, or in 99% of the applications, vacuum insulation is used just as a means to provide better insulation. So in those applications, no, the jacket is not monitored. In the Freeport application, where some of that pipe or fair amount of that pipe I think was buried, and I got to be careful how much I speak to that. That wasn't my project, but that jacket was designed for containment. It was a stainless outer on that jacket, not carbon steel, and then the jackets themselves are tied to a common header that has an appropriately sized relief protection. I can't speak to whether or not the vacuum itself was monitored actively. I don't know. But there's certainly there's the ability to do that. Full containment's a great question because that's been coming up more and more. Typically, vacuum insulated pipe for large bore or LNG applications is looked at. Typically, it's more expensive than foam insulated pipe. So what our customers are asking is if we pay the premium for the vacuum insulation for the superior insulation qualities, then let's get to the point where it's providing full containment, and that's possible. You just got to make sure your outer is designed to accommodate the thermal loads, and then provide appropriate relief mechanisms to make sure that the outer is protected as well. Yep. All right.
Thank you, Matt. I believe it's time for a break. Why don't we go 15 minutes? So I'll be back in 15 minutes, please. If I could ask you to return to your seats, please, we'll get started in a minute or two. Alrighty, we'll get started. Our next guest speaker is Jim Hogan. Jim Hogan has been the project manager of the Puget Sound Energy Tacoma LNG project since 2012. He has 25 years of engineering and project management experience, including a prior LNG project for PSE, hydroelectric and combustion turbine power plant projects, fuel storage and delivery systems, marine infrastructure, and specialty facility construction in the United States and Europe. Jim has a BS in mechanical engineering from Washington State University. Please join me in welcoming Jim Hogan. Thank you.
Thanks, Joe. Also like to thank Julie and the PHMSA team for having us here today and putting together this good group. So what I was hoping to talk about today is just give you a real quick overview of who we are, Puget Sound Energy, or PSE, the drivers behind our project, an overview of the project, and then a few challenges that we've seen or are still overcoming, and then conclusions and lessons learned. And one of the nice things about being later in the day is a lot of the challenges that I was going to talk about have already been discussed by others. So I will either skip over them or add to them and get you out of here that much faster. So the Tacoma LNG project is a combination utility peak shaver and transportation fuel supply project. And I believe it's one of the first, if not the only, new project in the United States that is specifically set out from the beginning to be both a utility peak shaver and a transportation LNG fuel provider. So who we are, Puget Sound Energy is the local gas and electric utility for Western Washington. We're the largest and oldest utility in the state. We are a privately held, investor-owned utility. We have a little over 1 million electric customers and about 800,000 natural gas customers. We are a traditional utility in that we operate a fleet of power plants, combustion turbines. I think we're the second or third largest wind farm operator in the United States. On the gas side, we operate an LNG satellite facility. We also operate a propane air peak shaver, and we operate a large underground gas storage facility. Essentially, we like to think of ourselves as just the hometown energy provider for Western Washington. So our project really has 3 drivers that came all together for us to look at building this plant. First was environmental, second was economic, and lastly was a resource supply issue. And so from an environmental standpoint, I think I don't need to tell this group that natural gas obviously is the cleanest burning fossil fuel. As a gas utility, we do like to emphasize the use of compressed natural gas vehicles and conversion of homes to gas heat for fuel efficiency and so on and so forth. In the Puget Sound region, we have a fairly high rate of CNG usage as fuel for garbage trucks, transit buses, things like that. And so Washington State and the Puget Sound region in general, we're kind of a green part of the country. These types of things really have a lot of importance to our stakeholders. So the real environmental issue that really started this project was the advent of emission control areas. And back in around 2010, the U.S. entered into a treaty that required the creation of these ecozones around the coastal areas of North America. And what these are essentially is within 200 miles from shore, this required reductions in both SOx and NOx emissions from ships operating within these areas. And so from a sulfur standpoint, really it drove a significant reduction in the sulfur content of diesel fuel from 1.5% down to 0.1%. And you might be asking yourself, what does a utility care about this? Well, the reason we care is that we have a shipping company in our service area that operates 2 ships a week from Tacoma to Anchorage, Alaska. And their entire transit is within that ecozone. So fuel is the largest cost for shipping. And so this company suddenly found themselves in need of becoming compliant with the ecozones. Other vessels that come in from China and come into our ports of Seattle and Port of Tacoma can burn typical marine fuel until they get into that ecozone, and then they'll burn more expensive compliant fuel. But for a company that operates completely within the ECA, this is a huge issue. So Toad is a very forward-thinking environmental company. They operate 2 ships from Jacksonville to Puerto Rico and 2 ships from Tacoma to Anchorage. And the decision they made back in 2011, 2012 was to build 2 brand new Marlin-class vessels for Jacksonville. And you've heard some earlier speakers talk about Jacksonville. They've got both those vessels in service in the last few months. And then their 2 Orca-class vessels that operate out of Tacoma are relatively new vessels. And they made the decision to convert those over to LNG, which is not a small task. It involves putting them in a shipyard for 3 or 4 months, new engines, the works. And as part of that, they went out to the industry and solicited for LNG supply in both Jacksonville and Tacoma. And so for Tacoma, we competed with a number of other companies for the supply of the tote vessels, and ultimately we won, which was one of the basic market drivers for this project. So you can see with the emission reductions that come with converting the Orcas over to LNG, it's not an insignificant thing. Pretty much an entire reduction of SOx, almost entire reduction of particulate matter, huge reduction in NOx, and then also CO2. And so, as I mentioned, to convert their vessels, they were adding the 2 green LNG tanks after the house, 4 new engines, and the associated fuel handling systems. Additionally, from our standpoint, we also have had other people coming to us. The Washington State Ferries, which is the largest ferry operation in the United States, has been working through the process of trying to convert 6 of their Issaquah class ferries to LNG. So they've come to us. That project takes a lot of work in our state legislature, and it may be a number of years before that's complete. Obviously, tote. We're starting to see some penetration in the trucking market in the Seattle-Tacoma area. Not as big as some of the other areas in the southeast, but we are starting to see some truck fleets. And then also our own service provider companies that build our gas and electric system are currently operating something on the order of 60 to 80 natural gas powered trucks that use LNG rather than CNG. So the market penetration from trucks is small, but it's there, and clearly the fuel usage is not as much as a ship. But it was enough to get our owners and our board of directors interested in pursuing this project. The one thing that gets talked about all the time with LNG as a fuel is the chicken and egg scenario. The infrastructure investment, both as a fuel supplier, i.e. us, and as a fuel user, for a new build or conversion to LNG is significant. So no shipping company is going to go out and spend tens of millions of dollars to convert a ship to LNG unless they know they have a fuel source. And no merchant company or even no utility is going to go out and spend hundreds of millions of dollars to build an LNG facility if we don't have a fuel customer. In addition to that, I think I looked this morning and oil was around $48 a barrel. That makes conversion a lot less attractive. When we started this project back in 2012, oil was in the $100 a barrel range, and we were looking at diesel gallon equivalents of LNG for the trucking market at a little over $2 a diesel gallon equivalent versus $4 diesel. Obviously that environment doesn't exist anymore, but when you're investing in something like this with a plant that has a 50-year life, you've got to take a long-term view. So for us, part of the reason we're in this unique situation is we have a marine customer that takes 900,000 gallons a week of LNG from us, and then we also have a traditional utility peak shaving component. So this is a 3-year strip of our gas send out, and the Pacific Northwest is a relatively minor climate, or moderate climate rather, so we don't have the huge long cold winters like you see in the Northeast or the Midwest, but we do still have some fairly decent peaks that occur every few years. And so along with our other gas peaking resources, this plant just helps add to our portfolio of peak shaving capabilities. And another issue here with combining the two uses is a typical peak shaver will have a large tank and a relatively small liquefier because you've got all summer, spring to refill your tank. And a typical, if there is such a thing, as a typical fuel supply plant would have a large liquefier, but there's not that much need for storage because you've got potentially a customer like Tote that's taking 1 million gallons a week. In this case, we're able to combine the two. We've got a tank that serves mostly our utility customers as a peak shaver, and we've got a liquefier that serves mostly our transportation customers. So what that allows is it allows our utility customers to get a peak shaver a little bit cheaper than we would otherwise be able to build one, and it allows our transportation customers to get transportation fuel a little bit cheaper than if we had a purpose-built plant. So our plant, we have an 8 million gallon full containment concrete tank on seismic isolators. And yes, if you're asking, that is very expensive. But we're kind of driven by our site and our seismic location to do that. We have a 250,000 gallon per day liquefier, 66,000 per day decatherm vaporizer. We have a couple truck racks, and then we have a direct fuel line to the tote shipping terminal that allows us to pump directly from the tank to the ship. And I'll show you a little bit more of that in a minute. This is the Port of Tacoma. It's an industrial port. Ports measure their size based on the number of tonnage of ships that come in, or the number of containers that come in, and depending on which ranking you get, they're on different levels, but it's suffice to say the Port of Tacoma is one of the top 10, if not top 5 busiest container terminals and break bulk terminals in the country. It's heavily industrialized. We've got a refinery in the port, we've got tank farms, we've got manufacturing facilities, in addition to a large number of the cars coming from Asia come in through this port, and then there's also container terminals, of course. Our site is in red. It's a 30-acre site, 30 acres of upland, and we have 3 acres of water lease. We were not able to find a piece of property to buy in the port, so we are a tenant of the Port of Tacoma, which is a governmental entity within the city of Tacoma. So here's a little bit closer view of our site, again outlined in red. You can see the tote terminal is directly across the street from us. And I should mention the tote vessels that we serve in Tacoma are trailer vessels, so they, as opposed to a container terminal that loads containers on and off, they drive trailers onto their ships, and each one of their ships can hold 600 trailers and 200 cars, and that happens twice a week. So their terminal is essentially a large parking lot. The existing site was a lot of things in its past. It was most recently a naval facility. It's been closed for a number of years, and with the exception of 2 buildings, we'll be demolishing everything on the site right now. Everything's vacant except for myself and my associate project manager have an office there, so we have about 400,000 square feet between the 2 of us, so it's pretty easy to get along when you have that much space. Looking down from the hill, this is a photo of the site as it is now. Again, you can see the port is very industrial. The large warehouse is the most predominant feature. And when we complete the plant, the view will be dominated by our tank. It's an 8 million gallon tank with about a 1-to-1 aspect ratio. So it's about 140 feet tall and about 130 feet in diameter. Otherwise, the plant is relatively straightforward. It is a mixed refrigerant plant. Again, the tank is the most prominent feature. We've got a single train, and then truck loading facilities, and then also a below-grade pipeline that runs across the street to tote. And that, by the way, was something that I had to get a waiver for, and that was a process that has taken most of the last 3 years. And that kind of gets into the fact of some of the things that we talked about this morning, that the newer versions of NFPA 59A allow you to do things like below-grade piping that aren't currently envisioned in the existing code. So we have an 800-foot-long pipeline, which is probably the most expensive 800 feet of pipe that I'm familiar with in the world, that goes from our facility across to tote. Whoops. And I'm zooming out here. You can see, again, a little bit closer, the tow facility. We daylight from the underground line. We bring it up onto this new pier that we are building. And the pier will have a loading arm on the end of it. Right now, it's just represented by a mast on the end. We just placed the purchase order for our loading arm a few weeks ago. So at the time this was made, we didn't have a graphic depiction of it. And the reason this is such a strange shaped structure is that we have to work around mooring lines, and also the tidal changes when the ship is in port. So the tide fluctuation in the Port of Tacoma is about 20 feet. At any given time during our fueling operation, the tide may move, say, up to 4 or 5 feet. So we have to be able to reach up and over the loading arm, up and over the mooring lines, because their fueling manifold is right on the aft end of the ship. And we also have to be able to accommodate tidal changes while the ship is in port. So that's the site really. As far as challenges, the Pacific Northwest is not the easiest place to build things. We have some of the most stringent environmental regulations in the country, particularly air, stormwater, marine requirements, etc. And so for the last 4 years, we've been working on all of the necessary permits. We are just about there, and we expect to break ground in August or September, but it has been quite a mix of agencies that we've had to work with on all levels of government. Building a facility like this in an existing port has also been very challenging. The marine terminals for import and export, you see, as one of the speakers mentioned, have thousands of acres of property. We have a 30-acre piece of property in the existing port. And that presented a number of challenges. I mentioned before, number one, the land cost is very high. This is prime waterfront industrial property, and they don't make waterfront property anymore. So we were forced to find an area that we are leasing. We also looked at purchasing pieces of property. It is a relatively populated environment. There's a lot going on in the port, which requires a small footprint, tighter exclusion zones, which is what drove us to a full containment concrete tank. It's really, for the volume of LNG that we need, it's really the only type of tank that would fit on this footprint. And then also, we are at the end of a peninsula. We're feeding this plant off of our distribution system. So by the time the pipeline gets out to our plant, we are not at the operating pressure of our liquefier. So we also have to add inlet compression, as opposed to building an LNG facility next to a transmission line or a higher pressure line where you don't need inlet compression. Also, due to the fact that we are at a dead end, we can't liquefy and vaporize at the same time. So on those days that we need to vaporize during the year, we have to shut down the liquefier. And then also, as we pull heavies out of the system during the liquefaction process, with a typical LNG plant, you would just re-inject those back into the pipeline. We have to do something else with them. And we're still working on whether or not there's a market for some industrial user that would like to buy the heavies, or if we will truck them back to a larger line and inject them back in, or I may sell conversion kits to convert barbecues to heavier gases, and maybe we'll sell to the barbecue market. I don't know. We're still figuring that out. And then lastly, the port is a man-made facility. It's a dredged facility, and therefore the geotechnical characteristics of the site are poor. Essentially, we're also in one of the highest seismic zones in North America, if not the world. And so our failure mode for the Port of Tacoma is complete liquefaction of the soil for our design event, meaning the Port of Tacoma will no longer exist, and probably a lot of the city of Tacoma will not exist. So for that, we have some pretty extensive geotechnical work we're doing. We're installing about 2,200 auger cast in place grout piles that are 3 feet in diameter and either 80 or 100 feet in depth. And we had to go nationwide just to find a contractor that could do auger cast in place piles of that length and depth. So basically what we are doing is we are creating a man-made island that resists liquefaction, and for the design seismic event, our plant will be there, but there will be no way to drive to it or nothing left around it. It sounds extreme, but as those of you that are familiar with the seismic design requirements for LNG, they are pretty significant. From commercial challenges, really the biggest thing that we learned is we're a utility, we're all utility people. The marine industry is extremely different. They use different words, they have different history, particularly in contracting. We're used to long-term take-or-pay contracts, 20 years or better. The marine industry likes to pay with a credit card to fuel their ships right at that time. So it takes a fair amount of negotiation and some creative and collaborative ideas to make things work. I had lunch a few weeks ago with another large marine customer that was interested in some off-tank from our plant. And we started talking about contracts, and I said, well, we like long-term contracts. And they said, yeah, we're open to long-term contracts as well. I said, well, what's your idea of a long-term contract? And the answer was 5 years. So we're miles apart, but certainly we made it work with Tote. Another issue is even the units that we use are different. Our contract with TOTE is in BOEs, which is barrel of oil equivalent of IFO 380, which is a marine fuel at the lower heating value. Us gas utility people, we're used to thinking in MMBTUs at higher heating values. There are some significant conversions that need to take place, and it may sound like it's not that big a deal, but I'll be honest with you, when we were doing our proposal to TOTE, I made a mistake between higher heating value and lower heating value, and we came up with some numbers that just didn't look quite right, and it could have probably cost us the project if it hadn't been caught. So again, the marine world wants to do things the way the marine world has always done them. They want the same contract terms, they want the same units, they want the same bunkering procedures, they want the same custody transfer procedures. So we have to adapt to them as the customer, and so it's been a learning experience for us. I won't belabor this, but as a marine facility, I know the import-export terminals have been through all this before, but this is new to us. We follow under both the PHMSA and Coast Guard regulations, and there are some conflicts between them. They're similar and not so difficult that we can't get through it, but from an owner-operator that's going to be audited by both these agencies, there are a number of small things you have to work out. And then, again, I won't even talk much on this, but the regulatory lag has been an issue for us, mainly with the Coast Guard and PHMSA. There's an understanding of things and we can work things out, but the city of Tacoma has also wanted to be very involved in the 193 element of this plant, and they adopted 2009 NFPA 59A. So that is something that we have to work jointly with all of our regulators to figure out exactly what to do. But from a design standpoint and an operator standpoint, it does cause us some sleepless nights sometimes. So really what we've learned is, all in all, through all the regulatory bodies we've worked with, everyone is supportive of LNG and methane in general as a transportation fuel. Long-term partnerships are essential, and not just contractual relationships, but also just long-term partnerships, public sector, private sector, stakeholders, etc. I cannot emphasize enough how important it is to collaborate early and often with the stakeholders. We have done an incredible amount of public outreach on this project starting 4 years ago, and we still find that there are people that feel like they weren't reached out to enough, or they weren't reached out to early enough. So it really, I cannot emphasize enough how important it is to get out there in the community, Rotary Club meetings, neighborhood associations, etc., because people don't understand LNG, and they ask some very good questions, and they have a right to be nervous until you explain to them. And then lastly, like a lot of life, solid relationships are the keys to success. Really, the relationships that we have with our regulators, with our suppliers, with our design team. The LNG world is a small industry, as most of you know, and I think relationships are key, that we as the industry are all working together, and that we're also, not just as industry, but with regulators, we're working together. So with that, I will leave it up to Joe as to whether or not I should take questions now or later. Okay. Or seeing none, I'll be happy to sit down.
With Bob Cam with ABS Consulting. With regard to your challenge with the heavies, C3 and 4 and 5, is that due to a requirement of your customer for gas composition?
No, it's just a matter of the fact that the heavies drop out in our initial pass to the liquefier because they have a higher freezing point, so they can't make it all the way through the liquefier. And so typically you would just inject those back in. Ours are going into a tank. We'll have to hopefully sell them to someone.
I was thinking that because you're getting pipeline gas, that it would already be at the tariff that would be necessary, so the heavies would be gone.
So even with the tariff, you're going to have C5, C6, C7, some components. It's a small amount, but it's still, like CO2, we have to take it out because it won't make it all the way through the liquefier.
Okay, thank you. And then may I suggest to tie into what Professor Gosman said earlier, maybe you can give away that stuff to your people around the area for their barbecues.
There you go. I like the way you think. All right, thank you very much.
Our next speaker is Lad Falat. He is one of our own here at PHMSA. Lad is Director of Engineering Sciences and R&D for the U.S. Department of Transportation Office of Hazardous Materials Safety at PHMSA since February 2015. Previously, he served several roles at the Bureau of Engraving and Printing in the production and development of banknote features. Lad has over 20 years of experience in the private sector, including chemical safety, packaging, materials science, and corrosion engineering. He earned a PhD and BS in chemistry from the University of Maryland and Penn State, respectively. Let's all welcome Lad Falat. You have slides.
Thank you, Joe. And thank you for your attention this late in the afternoon. I'll try to keep it moving quickly so that we can end on time and give you a chance to enjoy the lovely Washington State weather. I will give you a quick overview of the regulations for the transportation of LNG and an idea of the direction for future R&D related to LNG that we're doing here at the Office of Hazardous Materials Safety. The Office of Hazardous Materials Safety regulates the transportation of hazardous materials, including LNG, in commerce by other than pipeline means. These regulations consist of CFR 49 CFR parts 100 to 180. And after more than a year at DOT, I'm still very much a student of these regulations. The Office of Hazmat Safety does not regulate stationary storage of LNG or its use as fuel on board vehicles, ships, trains, heavy equipment. We also do not regulate the transport of LNG and the large ships, the tankers, super tankers, what have you, which is the jurisdiction of the U.S. Coast Guard. Hazmat regulations are enforced very much in partnership with our other DOT modes, including Federal Railroad Administration, Federal Motor Carrier Safety Administration, the FAA, and of course Department of Homeland Security's U.S. Coast Guard. So 49 CFR parts 100 to 180 includes the hazardous materials table, section 172-101, which is a very extensive listing of all the hazardous materials, the transportation of which we regulate. The HMT, as it is known, lists methane refrigerated liquid as UN 1972, and it is classified for transportation as a flammable gas, class 2.1, no surprise there. Without going into a tutorial on the hazmat table, the hazmat table contains information on authorized packaging, and it contains exceptions and special provisions for transportation of individual hazardous materials. This methane refrigerated liquid, as we know it, has in the table a special provision T75, which means it is authorized to be transported in portable tanks in accordance with specification 178-277. These are insulated tanks with a minimum capacity of 450 liters or 119 gallons, although as most of you know, T75 tanks have been fabricated up to 40 feet in length with a volume capacity of 45,000 liters. The second special provision, TP5, specifies the fill rate and the outage for portable tanks. Outage simply meaning it's the percentage vapor space above the liquid phase. So back to the HMT, the hazmat table. Column 8 specifies packaging for transportation. LNG has no exceptions listed. It has no non-bulk packaging authorized. And for bulk packaging, section 173.318 is authorized, which is basically cryogenic cargo tanks for highway transport. And again, you've seen that here today. Column 9, which I don't have a slide for, specifically prohibits any air transportation of LNG for obvious reasons. And column 10, applying to vessels, specifies stowage D, above deck on a cargo vessel or a passenger carrying vessel with a restriction on the number of passengers, and also the stowed LNG containers must be clear of living quarters. Now, it is late in the afternoon, but you are a sharp group, and the fact that up to now I did not mention rail transport of LNG did not escape you. So the hazmat regulations do not authorize transport of LNG in a rail tank car at this time. This does not mean that it is not being worked on by the industry and regulators. However, portable tanks and cargo tanks are authorized on rail car, but only with the additional approval from the Federal Railroad Administration. In our regulations, section 174.63 specifies the requirements for rail transport of LNG in the above authorized packages. And for anyone interested more in the rail transport of LNG, I would refer you to our colleagues at the Federal Railroad Administration. Inland transportation of LNG is predominantly by highway at the moment in a fleet of vacuum insulated tanks and trailers with approximately 28,000 tanks and trailers operating. The safety record of LNG by highway is or has been nothing short of phenomenal, thanks in big part to the dedication of the regulated community to safety. Over the last 15 years, only 10 highway incidents have been reported to PHMSA. And as you can see from the additional stats up there, it is simply phenomenal that there haven't been larger incidents. So I only have a couple more slides which I would like to put in context for you. When the horizontal drilling in the Bakken region resulted in a huge increase in rail traffic of crude oil, and I mean like a 5,000% increase, the Office of Hazmat Safety was, and to a certain extent remains, in a reactionary mode in assessing and then working with Department of Energy and Federal Railroad, Transport Canada, as well as the energy producers and the rail industry, in minimizing the hazards. There were probably economic indicators which may have predicted the sudden increase in crude by rail. But this time we are committed to watch those economic indicators and to be much more proactive should a crude oil type revolution occur with LNG if it hasn't started already. Just in the past year, Hazmat has begun to collaborate much more with Federal Rail and the Office of Pipeline Safety in terms of leveraging each other's R&D and expertise on LNG transport. Our own Risk Data and Program Development Division is analyzing commodity flow to fully assess the impacts of safety from increases in transportation of energy products, including LNG. And we have also commissioned an exhaustive literature search on fire and impact testing of packaging that are authorized for transport. This includes re-examining test methods for assessing properties of steel used to fabricate these containers. And in collaboration with FRA, and I don't have it on the slide, but I want to emphasize, and industry groups, we are working to eventually establish a baseline rail tank car for LNG. PHMSA has commissioned DOT's own Volpe Research Center to assess the impacts of small-scale LNG facility siting on its impact to LNG transportation safety by highway, and to perform some basic crash modeling. We are in the discussion phase with Federal Railroad to perform additional modeling on tank car collisions and do some additional larger scale fire testing on portable tanks. And here I'm going to repeat myself a bit, which is not necessarily a bad thing, on what is in our R&D future, which of course is to continue to build a stronger partnership with the Federal Railroad, to keep monitoring market conditions and energy products, and finally to issue our own broad agency announcement for research proposals, including for LNG transport, such as Pipeline already has and Federal Rail just issued a little while ago. The Office of Hazmat Safety recently held an R&D public forum describing our overall program and inviting research needs from the regulated community and the public. So I want to invite you to visit our R&D website and to provide us feedback, research needs, and proposals in all of our program areas. Thank you once again for your attention this late in the afternoon.
Any questions for Ladd, now that you sat down? All right. Well, that concludes our talks for today from our guest speakers. And I believe we're going to enter into an open discussion. Julie, is that right? And at this time, Ken Lee will give a little talk here. Thank you again.
How about let's have a round of applause for all of our excellent speakers today. Yeah, so we had many excellent presentations. I mean, I learned a lot. I hope you did too. They were very informative, engaging to help us better understand, this fast-changing LNG world. As Joe says, we will have an open discussion, and we welcome your questions at this time. For those of you who are on the webcast, feel free to use Twitter. You can tweet hashtag PHMSA, that is PHMSA LNG, or email pipelineforum@dot.gov. So if you have a question here, feel free to raise up your hand, and we have two people with microphones that can walk over to you.
Hi, I'm Alex Edmiston from Cosmodyne. We're a LNG plant supplier, and I have two questions. The first is, you've talked about some of the issues with trying to comply with older codes, and we find it nearly impossible to get some vendors to comply with both codes. They really want to use the latest edition of the ASME codes, for example, on vessels. And how we've been dealing with it is telling them, okay, use the latest edition of the code. However, we'd like to impose some additional pressure test requirements on you to comply with the more stringent 92 code. Is that enough?
We've been asked that question many times, and we've tried to address it by issuing an FAQ on our website that gives you a path to comply with regulations using the NFPA safety equivalency section in there. That is an interim step. We're working on rule making right now to try to create a more comprehensive solution to that.
Then my second question deals with the entire site. You have many different types of vessels. Some vessels have flammable liquid in them, others do not. Is there some kind of guidance on which vessels have to comply with the 193 code and which vessels can be treated as typical vessels?
Would maybe someone else like to answer that? Probably better than me, who's...
I mean, an example would be, a lube oil cooler on a air compressor being cooled by water. It happens to be on site. Does that have to comply with the 193 regs?
Is it? Let's get away from there. I'm Buddy Secor. That's not the intent. And if you want to talk to us directly, we certainly can. Joe Seavey has been working the issue. But what we're trying to do, and as Ken mentioned, refer to the FAQ. And if you have further questions, just give us a shout and we'll help you with that.
Okay. Thank you for your question. We have a website email here, and it states, for your information, the question that was presented to Jay about fueling standards for LNG, alternative fueled vehicles, NFPA 52 addresses this for the vehicle and for the fueling facility that may be linked with NFPA 30A. So that came from an email to address Jay Jablonski's presentation this morning about NFPA 59A.
Ted Gleigman, Center for Sustainable Economy. And it is not my goal to put PHMSA on the spot here, which is the kind of thing somebody says when they're about to do that. Please forgive me, because I really appreciate the fact that you put this together. It's been very informative and I think very helpful on a number of fronts. But it's sort of shocking, just to pick the one that's been so prominent today, that NFPA 2001 is the most recent version that has been incorporated into the federal regulatory regime. I mean, there is no one in this room who is still using a 2001 cell phone, for example. Has this been a function of understaffing and federal budget cuts, or are there other reasons why PHMSA has been unable to deal with the last 4 updates to NFPA 59A? Thank you.
Yeah, I think it's a very long history, which probably, would take too long to explain here, and which I'm not fully aware of the complete history. Many of you may be aware we did issue an advisory bulletin, I think about a decade ago, stating that we had issues with a newer, I think in 2009, we had issues with a newer edition of NFPA 59A. And so we took a look at, we considered adopting a newer edition of 59A, but we had some safety issues which we wanted addressed. And it has been kind of stalled since then.
Thank you. So there's an implication that not every reform in the new regulations is something that PHMSA has seen as a step forward in terms of protecting public safety. Did I understand you correctly on that?
Yeah, I think back in 2009, the staff here felt that there were some things that were better and some things that were worse safety-wise in a newer edition of NFPA 59A. And I think, since then, the LNG activity has not increased to the level that it has in recent years. So it wasn't a big top priority item. And it has become a huge issue industry-wide in the last few years as we're constructing all of these new LNG facilities.
Are you in a position at this point to speak to the question that you had to deal with the 2009 edition of whether the 2016 edition is uniformly a step or a set of many steps from the presentation this morning in the right direction in terms of overall improvements to public safety?
We have been in contact with NFPA, and we are doing a very diligent review over the current edition of NFPA 59A and comparing it to previous editions. And I think it's too early to say what the conclusion of that is going to be, but our engineering staff is doing a very comprehensive review detailing all of the main safety differences.
I was tardy this morning. I apologize, and I think I annoyed the security personnel by having too much stuff. So this may have been spoken to, but at this point, do you have a time frame projection for the completion of that review?
We are working diligently on that. It's a top priority. Unfortunately, I can't give you a time frame. Hopefully, we hope to have that finished soon. But it depends on what issues which we see that need to be overcome. So it's very difficult to predict.
So not even a rough guesstimate at this point?
I think I really shouldn't, give you an answer which has a good chance of being wrong.
That's very prudent. Thank you for the dialogue. I appreciate it very much.
Mark Mayday, Union Pacific Railroad. This question is going to be directed to Ladd. In your presentation, you made a statement about looking at an authorized package for methane refrigerated, that there would have to be a authorized package. We're already shipping cryogenic liquids in DOT 113 specification tank cars right now, classified 2.1. Is there, other than being an energy product, is there something that characteristically, when compared to like ethylene refrigerated, that it's dramatically different?
While I can't answer you specifically because I'm not that familiar with the differences, in discussions between Office of Hazmat Safety and FRA, we have identified that we simply can't take an existing cryo car and put it in LNG service. But again, I would have to defer for the specifics to the FRA. Although that is one of our higher priority areas to develop specifications for a LNG rail tank car.
We have a email question here, and it says, we want to know how PHMSA will address buried LNG tanks like at a LNG production plant that produces motor fuel and LNG fuel distribution like a truck stop and puts its boil-off gas into the local distribution system. So I think this is a good question which we will need to research to give a good answer. So we will research this and reply back at a later time.
Hi, again, it's Cecile Schofield. In 2010, PHMSA changed its requirements for flammable gas vapor dispersion. Up until that time, LNG developers were using a modeling called Source 5 modeling. And it was as a result of work that two young men from Fall River, Massachusetts did. They pointed out to PHMSA that actually that Source 5 modeling contained flawed data. So what PHMSA did was, I guess you notified FERC, and FERC sent letters to all of the LNG developers and notified them that if they had used Source 5 modeling methodology, their project was basically put on hold until they could meet the new requirements. And I recall reading a complaint from one such LNG facility developer who complained they didn't think it was fair that now suddenly their project had to meet a new requirement where they had been approved under the Source 5 modeling. And I recall PHMSA's response, I have a copy of the letter, to the effect that when it comes to public safety, they were going to have to meet the new requirement. So that kind of ties in with one of my earlier questions, where the LNG developer in my county in Florida is using the 2001 edition of NFPA 59A, when we know that the risk-based edition, 2013, it really serves to greater protect the public. It includes so many things like leak and piping, storage arm. It's risk-based. And so my question to you is, why would you allow a new facility or a new tank to be constructed with 2001 when we know 2013 would really protect me and my family? Thank you.
Julie, do you want to take a shot at that?
Sure. Risk-based and prescriptive, is, I think Sarah gave a good presentation on, are two different approaches. So today we have an exclusion zone, which is prescriptive, and we're looking at the possibility of a QRA. So I guess you can't really compare them apples to apples. They're two different approaches. A risk-based doesn't necessarily mean you're going to get a different answer to the size of your exclusion zone. You're looking at it based on frequency failure rates, on the likelihood of events, of the consequences happening, or the size of the consequence, as opposed to prescriptive regulations where there's been that analysis done in the background. So, we would hire people who have expertise in that field to then develop essentially a table, really more than having each individual operator go and do an assessment of that frequency failure and the consequences. So one's just a one-size-fits-all, and the other is a individual site-specific look, but you're not necessarily going to get different answers. One's not necessarily better than the other.
Julie, I will add, and a good question, good comment, is we have a study underway with Oak Ridge National Labs regarding risk citing and whatnot. We're going to be talking about it extensively tomorrow. We have several speakers, so stay tuned. There'll be maybe some of your questions be answered.
I know there are substantive differences between the two.
Yeah, thank you so much for that's a very good quick question. And the regulations hasn't changed in many years, and this is one of the reasons why we're having this workshop to find out what your concerns are and what the needs are in new regulations. So thank you.
Hey, Terrence Wells, Lloyd's Register. I just wanted to invite a question that might be better answered tomorrow. I just want to maybe understand sort of what the move forward path is for the redevelopment or the advancement or update of the regulation.
Yeah, there's a fairly strict federal government rules on how regulations are written and developed. This is really one of the first steps. There will be it could be a notice of proposed rule making, which will be, announced on the Federal Register and on the internet. There'll be public comment periods. So this may be the first of many events, public, your chance to comment, for new regulations. But it's a fairly complicated, strict process that the federal government goes through in its rulemaking. And it often takes, a long time, many months or sometimes, many years, where we have to address, the comments that we receive from the public, industry, and everybody else. And it has to go through things like, cost-benefit analysis, and it has to be approved and passed by many levels of government. We have a question by email here that asks, can we expect to see standardized exclusion zones for certain size ASME tanks in the new version? I think, that's one of the things which we will consider. We'll add this to the list of issues which we're going to discuss, unless, Buddy or Julie has any other comments about this.
Well, that's one of the other speakers earlier talked about within the code. There's, I believe it's chapter 13 about shop fabricated. So there already is within the code a recognition of smaller scale, but we haven't necessarily adopted that. But as Ken said, that's something that we're looking at now as our review.
Thank you. Nino Nicotra from Bechtel. I agree with you that the system we have at the moment is safe enough if we compare with QRA in terms of risk to the public. I wonder if in the future you're going to take into account a level of tolerability of the risk of the public. And we have not been looking at the risk to the individuals working in the facility so far. Typically, we look also at individual risk for work groups. Is there anything that you're going to do in the future about workers?
Would you like to take that, Julie?
So tomorrow you're going to hear some discussions on process safety management, and that's obviously looking as well at the worker safety and the risk. So there's many, again, different approaches. Which approach we'll go with has a lot to do with our analysis and the comments that we get from you guys via the Federal Register, which if you look at the back of the program, it provides how to submit those comments. Does that answer your question? Oh, and the tolerance to the risk of the public. So, I think you would get varying perspectives if you asked people in here, is essentially zero risk to the public too overly risk adverse? And I think if you talk to the public, they might tell you that there's still some risk to them, and maybe it's more that they haven't been a part of that process of understanding what the risk is. But that's all part of the QRA work that Buddy mentioned.
Hi, Jenny Mandel with the Energy Wire. One thing that I'm still not clear on, and maybe this will be touched on tomorrow, is to what extent the changes of the next couple of years will apply to existing plants, if at all, versus to new plants, both plants that are already built and plants that are, say, in the regulatory process. I think that once they've entered filing at FERC for the large-scale plants, they wouldn't be governed by new regulations. Is that right? Can you speak a little to that?
Can you repeat the last part of the question regarding FERC?
Sorry, just whether for plants under FERC's jurisdiction, if they enter the filing process before new regulations are finalized, my understanding is they would not be subject to the new regulations. Just can you confirm that? So they would be covered sort of the same way any existing plant is? Is that correct?
Thank you so much for your question. That's a very good, quick question. I think it's too early to say, where the rulemaking process is going to go or what it's going to be covered. Like I said, it's a pretty comprehensive process, and and there is a cost-benefit milestone that it has to go through. And so when it covers existing facilities, the cost may be substantially more than if it applies to just new ones going forward. So I think it's too early to say what the new regulations are going to be, what's going to pass cost benefit, and what that picture is going to look like. So obviously, it may cost a lot more money, to retrofit or to convert older facilities than to make the change before you start design and construction.
And sorry, just for that last point, as far as facilities that are under development, when the regulations change, if assuming that they do in fact change in the next year or two, would those be lumped with, those would have a cost-benefit analysis together with already built facilities? Is that right?
The cost-benefit, the benchmark is the present regulations. So it's any delta that change. So you need to have whatever the new regulations are going to be. That has to be justified by the benefits has to outweigh the cost, essentially.
Of course. I'm sorry. I'm having trouble conveying my question. It's that imagine that there's a facility that enters the FERC filing process a year from now, the formal filing process, and a new regulation as a result of this process and the ongoing review at PHMSA, a new regulation is issued a year and a half from now. Will that project be covered under the old regulation, the 2001 59A standards, along with anything that's already been built?
I don't know the answer to that question. I mean, would someone else like to take a shot at that?
I'm Alan Mayberry. That would be covered in the process as we develop the regulation. How retroactivity, which facilities are covered retroactively, versus which ones are covered by the new reg. That's something we deal with any new regulation, so it would be addressed. But we don't have an answer for you right now to your specific application because the policy's just not been developed yet, and how it would apply to new versus old. But that would be addressed through our rulemaking process.
As you take a look at evaluating the new code and what it's involved, is it going to be an all or none type thing? Is it going to be NFPA 2001 or NFPA 2013 or NFPA 2016? Or is it going to be something where you say, well, it's NFPA 2001, but we're going to update the vessel code to the new standards?
Thank you. That's a very good question. And what we can do a full incorporation where we incorporate the entire document, or we can also incorporate only certain sections, which we do currently with certain standards. So we could either incorporate it all, incorporate none, or incorporate some, and make specific references only to certain sections that are applicable. Currently now, we do reference certain sections of NFPA 59A 2006. So there's certain limited references only to specific sections of certain editions. Any more questions? Is there anything from the webcast? Any questions from? Okay, great. Thank you, everyone. Now, Buddy Secor will wrap up and give some closing remarks.
Good afternoon again, everybody. Thank you, Ken. I'm Buddy Secor. I'm the Engineering Operations Supervisor for the LNG Group. I wanted to put that in perspective. You've met everybody in the LNG Group today. Joe Seavey, who was introduced to everybody. Joe, wave your hand one more time. He does a lot of project reviews. Julie Halliday. Julie, where'd you go? Right here. She's been passing the mic every day. And myself, and Ken Zaid Obaidi over here keeping notes. He's helps me part-time with project management. I do project management coordination and whatnot because they don't want me to get too close to the technical stuff. So they promoted me to supervisor. So that worked out pretty good. Bear with me just a few minutes, not very long. I know you're tired. Thank you for bearing with us all day long. I know it's kind of tough to sit in a seat for the balance of the day, but I think that it was a very productive time frame. We heard a lot of good speakers today. We'll hear many more tomorrow. What I want to stress, and I've been to a lot of conferences, you probably have too, where the second day you want to bolt and run. Take a look at that agenda. You may not want to. There are some very good things that we actually stacked in the deck to help persuade you to stay. So many things. Let me hit some of the highlights here, find my notes. But again, thank you so very much for being here. We've got small scale risk tomorrow. We've got discussion of incidents and emergency response. Many other things. You can take your agenda and take a look. Statistically, I just share with you, we had 360 attend today, 160 in the room and 200 online. That's pretty significant. What that tells us is this is very, very important. And we take it very seriously. We record everything. If you want to sit through this again and watch it on YouTube, it will be available to you. So 2 good solid days of sitting there if you want to go through it again. But we record it for our sake so that we don't miss anything. We have Jeff Marks in the corner taking notes. But even after tomorrow, this won't be your last opportunity. We're going to have the opportunity for you to send in your formal response and your comments and questions to the docket number. Rulemaking is very long and intensive, but we haven't set our mind on anything. So if you ask us questions now and we seem a little confused, this presentation was all about open ears and hearing what you all have to say. So please give us your input and your feedback. We know that there needs to be change. Now, housekeeping for tomorrow. You survived the gauntlet today getting through security. It will not be any different tomorrow. But if you're traveling and you have a bag, be aware that our security is probably going to go through your bag. So it might be advisable to try to leave that behind at the hotel and minimize what you bring through here. Get here early because this is a federal building and it just simply takes time to go through security. That's about all I want to do. I do want to recognize one person specifically. Julie, who handles a lot of the LNG matters and is going to take the lead in our regulatory changes and whatnot going forward and working with NFPA 59 committee and whatnot, put this conference together. And if you've ever done this sort of thing, you know how very painful and hard and the devil in the details it is. So if you would mind, let's thank her for that. That's about all I have. Now, you'll need to go out the way you came in, surrender your badge, and we will re-register you tomorrow. So thank you very much for your attendance today.